Hi guys, welcome back to the series of tutorial on databases. Today we're gonna delve into a little bit more on the data entry part. So how do we put data? Into data.base, which is our main object, let's say, especially if we need to take some element and segment it or analyze it in some way. And again, the point is that datasets are kind of general. You can put audio features in them, but you can also put score features, you can put textual features, you can put images features, and so on. So it's kind of up to you what you mean for segmentation and analysis. I will give some examples, but those examples are just a very narrow possibility among many more. I hope you see the process more than the content. As an example, suppose I have a folder containing a lot of short sounds of ticks. I do have it on my hard drive. I can put a link to it. I want to analyze them and to add them to a database. And the first thing I need to know is what kind of analysis I want to perform on them. And this also requires some tools which are actually capable of doing that kind of analysis. We have, for instance, three kinds of tools I can maybe mention that are capable of analyzing audio data and buffers in particular. Those are, I'd say, the orchidea.features module. You can find it in online, I think at this is handy because you can give it either a buffer or a file name. I will just spit out the average, centroid, and spread. In this case, you can put the feature as argument. The downside is that it doesn't really have many features to choose from. My best option is usually descriptors by Alex Harker because in this case, the number of descriptors is higher. You can look up in the help file. Again, this one can be found in the Alex Harker's web page. But as for now, it might be not the case when you see the video, but as for now, the release which is publicly available, I think it only supports 32 bits, which means that you cannot use it on max 8 as far as I know. That's the downside of using descriptors. We are gonna use for this example IRCAM descriptor, which again is a good descriptor tool by IRCAM. You can find it at this address, and it has a mountain, I'd say, of descriptors, a lot of them. The downside is that, as far as I know, it doesn't have a way to ask for an average descriptor of a buffer. What we have to give is the analyze buffer message to analyze a buffer. It cannot analyze a sound file, it has to analyze a buffer, so we have to import the file into a buffer. We can do that with load mass replace. For instance, if we want to analyze this file, which just have a short tick at the beginning, we can replace the buffer and we can use IRCAM descriptor asking for these descriptors, loudness, spectrum, centroid, and spread, for instance. So we send an analyze buffer, which spits out actually the loudness, spectrum, centroid, and spread, but window by window. If I put a print object here, for instance, we can see that the loudness is spit out window by window. So this is the loudness of the first analysis window, and so on for every analysis window. We can then ourselves, we need to make the average was ourselves in a sense, and we do that by only taking this is a rough estimate. It's a really rough estimate. We take only when the loudness is greater than 0, then we estimate that the spectral, centroid, and spread are meaningful values, and the loudness itself. We make the average, so we remove the silence in a sense, and those are the average. And I want to stress out that this is not necessarily the same as the average given by other descriptor tools. So if we do the same with Alex Harker, this is the average centroid, for instance, in Hertz. And that's the same with orchidea.features. Even using the same parameters, FFT parameters, you see that we get, those are kind of similar. And this is massively different, on the other hand. And that has nothing to do with our greater than zero, because if we remove it, those mean it's probably going to go down if we remove that. And we just let everything through. I suppose that everything, this is going through, but as you see, this is even lower, because all the silence is gonna bring down the spectral centroid. So, but what I mean is that you have to choose the tool that suits your needs. So you have to choose carefully your analysis tool, and this is not a tutorial on how to do that. This is a tutorial on how, when you have chosen your analysis tool, how can I use it in order to build a database. And so how can I use it? Suppose we choose the IRCAM descriptor tool, and then we want to build a dataset of analysis of our samples. Well, first of all, we need a database, MyDB again, that's a common name. And when we need to add a table, we add the samples table with all these entries: file name, duration, centroid, loudness, spread, and let's say type. We will distinguish between 3 types of sounds: the low ones, the mid ones, and the high ones, let's suppose so. And then we want to analyze the whole folder. So what we can do is to use bach.path to LLLL, which will take a path and spit out all the items in the path. Since I have 2 outlets, I can wonder what they are for. The first one is for relative paths, and the second one is for absolute path or full path. We take this one. We want the full path of the items in order to iterate on them. And one by one, we put them in a buffer, okay? And we take the duration of the buffer via info. When the buffer has been filled, we ask for the duration to info tilde, and we get the duration. And then we analyze the buffer. Since it has been replaced, we analyze the buffer. And what we do is the same thing we did here, only we have encapsulated it in a patch called p.analyze, but it's exactly the same. So we take the average loudness, average centroid, and average spread. And given the average centroid, we split into 3 cases. If it's between 0 and 2000, we say it's low. If it's between 2000 and 4000, we say it's mid. And otherwise, we'd say it's high. And so we fill also the type column. And we fill the file name at the end. So we use backpack for that. That's kind of convenient because it structures the LLLL exactly as we need in order to be given to data.base. We have to be careful because we have still to prepend the add entry message, and then we have to give the table in which we have to put the entries, the samples table. So add entry samples, and then all the content coming from backpack. So whenever I click on that, all my database has been populated by analysis, and I can see it if I double click. Those are the analyses. Very well. If I want to clear them, I can clear them. If I want to, and there's nothing there. And if I want to do that again, I'll just click and I'll do the analysis. This is another example where we need to also perform some segmentation. In the case before, we didn't have to perform any segmentation on sound files, meaning that I already had them and that's it. I had collection of sound files. Each sound file is an entry. Now, what if I only have one long sound file and I want to chop it up into segments? Again, this is not a tutorial on how to chop it up. There are a lot of ways you can do that. I'm putting here in the bottom right position some of the items you can Google in order to perform segmentation. You can use, for instance, the PIPO tools by IRCAM, or you can use the brand new Fluid tools by the Flucoma project of the University of Huddersfield. Or you can use maybe other tools of your choice, the Mubu tools, which are a friend of PIPO in a sense. Or anything else. You can segment that by hand in a sense and get a list of markers. But suppose we want to just crop equal portions of the sound file. So we are not using an elaborate algorithm to find the onset inside the sound file, but we just want to chop up the file into chunks of half a second each, let's say 500 milliseconds each. We might want to have a table named grains, let's say, with the file names, but in this case we need to keep track of the starting point in the file, the ending point, and the duration. We can just use two of them to deduce this third one, but well, we just keep track of them, it's easier. Then the centroid, the loudness, and the spread, so the three analysis features we want to use again. How do we do that? Well, we can take the file name and give it as the file name in bach.pack. It's not gonna change, so it's gonna stay the same for all of the items. Then we want to put the audio file inside a buffer. Once we have done that, we get the duration of the buffer, and we build an arithmetic series going from 0 to that duration with steps 500. Which is nice because it's gonna be 0, 500, 1000, 1500, and so on until the duration is reached. And then we group 2 by 2. Here we have, again, we're gonna have something like that, a plain list with something like that. Whereas here, we're gonna group the elements 2 by 2, but not like that. So we're gonna put a level of parentheses. It's not gonna be like this because there's an overlap 1 request. So it's gonna be like this. Elements are going to overlap by 1. And so on. This is convenient because those are the portions of a sound file I want to extract and analyze. Sorry, of course I made a mistake. This is gonna be like this. So for each one of these items, we want to extract this portion of sound file, for instance, between 0 and 500, and analyze it. We do that in a very, very, very stupid way because it's the easiest one to do in Max, but it's absolutely not the quickest one. By far, it's not the quickest one because we are using the crop message in the buffer. So we build another buffer named temp crop, where we are gonna store just the chunk of the buffer we want to analyze. And to just retrieve the chunk, we duplicate the buffer, and then we crop it to the right starting and ending time using $1 and $2. Again, this is not ideal because we are duplicating a whole buffer when we just need a portion of it. We are wasting a large amount of CPU, but again, this is just for demonstrative purposes. You can use a better way to do it, but this is a way of doing it. It's gonna be slow, but again, once you have cropped the right portion, we can analyze it exactly like before. And then we just need to give also the starting and ending points, but this is just the first and second element in the list, so we can unpack them because we have used at and wrap 1. So we take the first element, that's gonna be the starting point in milliseconds. The second element, it's gonna be the ending point, and the duration will be the difference between them. Well, we could have used this number as well since it's fixed, but then again, everything is like before, but when I do that, well, first I have to add the table. Notice if I add it twice, Max is gonna complain because there's already a table, so arrow creating table grains, no big deal. The table is there. And then we populate it with, in this case, I've used a public domain Beethoven recording, but it's just an example. You can use the file you want of your choice. But once it's done, again, we have a database populated with all our this is the samples, but then we're going to have a grain table, as you see, grain ID, file name, start, duration, and so on. So we've analyzed the fragments of our large file without needing to have many files. We just have one, and we've analyzed all of it. I want to also give some more examples of things you can do. Instead of chopping up audio files, you can chop up scores. In order to do that, you can use data.segment, which is a convenient tool because it segments. It's a segmentation tool for scores, which also is able to perform analysis in a lambda loop manner. So you have some predefined analysis modules, like getting the centroid of a score, which is just the average pitch, or the energy, the total energy of a score, which is a sort of measure of the average velocity, I would say. But this is exactly the same thing as before. So there's an entry score, except that the mechanism is a bit more complex. I won't go into details here because I will dedicate some more tutorials to data.segment in the future videos. But I already wanted to show you, because if you want to get into it, you have this patch to start from. Data.segments outputs the segmented scores in a list and the corresponding features here. So we can iterate on them and join them properly in order to format the list for data.base. As final example, you are not bound to use datasets for music or for audio or scores. Again, you can use them for words, for images, for whatever you like, for videos. This is an example we can build a table of, name it Alice, with the occurrences of words in the first chapter of Alice in the Wonderland by Lewis Carroll, and also an analysis whether the word is a palindrome or not. We can do that by retrieving all the words. There's a subpatch here. Again, I'm not entering into details here because it's not relevant for the database. You have the patch if you want to inspect it more. We are retrieving all the words here. It's just a list of words. We take the list of words and then we sort it. And then we split it whenever it changes. This is kind of a convenient way to split a list whenever it changes. For instance, if I have a list which is AA, sorry, it's hard to make an A, baby, baby, and CC, and I pass it through here, and I put a back.print, well, here again, I'm just grouping all the equal elements into brackets. That's a convenient way of doing that. And once I've done that, well, I'll just take again all the elements one by one at the root level. So all the lists, I unwrap them all, and the number of occurrences of the words is just the length of the list. So if I have 6A, it's gonna be 6 for A. If I have 5B, it's gonna be 5. And this is a very easy way to see whether the word is a palindrome. I take the word, I convert it into an integer list, into ASCII probably, because we're gonna use ASCII codes. I reverse it and I verify whether the reversal and the original list are the same. If yes, that's a palindrome. If no, that's not. In this way, I can build a dataset of entries. And also, if you are curious, there's an object named bach.wordCloud, which can represent word clouds. You can look up, you can inspect also this little patch that builds the word cloud, if you're curious. And that's it. That's it for today. I hope you learned something, and stay tuned for the next part of the series where we will learn how to query databases.